Hello, scholars. So a few things to remember here. When you have a function that's differentiable, meaning there is a derivative, okay, then you know that the function is definitely continuous. Meaning, if you graph that function, there's not going to be any jumps, holes, vertical asymptotes, any problems like that. Okay, now the other way doesn't always work. So you can have continuous functions that doesn't have a doesn't have a derivative. Okay, so not always differentiable, and it happens at the way I remember this is it happens at the pointy parts of a graph. For example, you see everything in this first graph is continuous except at this little pointy part right here. This pointy part here is continuous because there's no problem there, there's no hole, there's no asymptote, there's no jump. But this guy does not have a derivative. Okay? So the same as this pointy part right here, it is continuous, there's no problem, there's no hole, asymptote, no jump, but it's pointy. And there's no derivative there, just like here and just like here. Now you're like, why? Okay, well, a derivative means, remember this, that the slope of a tangent line. So if I look at the slope of this first line right here, this first line, if I take 2 points from it, this guy and this guy, the slope would be down 2 over 2. That means the slope here would be negative 2 over 2, which is negative 1, okay, for this line on the left. Now, from the line on the right, this line, the slope would be 1, 2, down 2 over 1. So that would be down 2 and left 1. Negative 2 over negative 1, that means 2. So 2 and negative 1, are those the same slopes? They're not, okay? So that means the slope on the left doesn't equal the slope on the right. Okay, so that's one way to think about why pointy parts of a graph is not always differentiable. It's not differentiable if it's pointy. Okay, so a way that you can write that in math is the limit as x approaches a number from the left of the derivative is not equal to the limit as x approaches the number from the right of that derivative. Okay, in other words, if there's a pointy part of the graph, it's not differentiable at that point, even if it's continuous. Okay, next thing. I know it's been a very long time, but this is the mean value theorem, and usually it's tested on the AP exam, and you need to know the certain parts of it, okay? The mean value theorem only applies if you have a function that's continuous and the function is also differentiable, meaning you're not only continuous, but you also have a derivative in there between the intervals, in the interval a to b. So this is a, this is b. I'm looking at this blue graph here, and in the blue graph, this line is continuous, there's no problem. There's no pointy part, so I know that it's differentiable. Great, so now we can apply the mean value theorem. Well, all the mean value theorem says is, if I take the slope of this graph on a to b, so that'll be f of b minus f of a over b minus a. This is just a slope formula. This is y2 minus y1 over x2 minus x1. So take a minute and pause. Make sure you know where I got these notations. Okay, so the mean value theorem just says this slope is equal to the derivative at some point in between. So that means if this slope was, let's say, 7 over 3, okay, I just made this value up, then somewhere in between a and b, there is an x value here, let's say here, such that this derivative, or the slope of this tangent line, is also 7 over 3. That's all this is saying. That's what the mean value theorem says, so MVT says that. Next up, Rolle's theorem. So Rolle's theorem is the same as above, but more specific, okay? It doesn't say that slope is equal to the derivative. It says that the derivative at some point will equal 0. So it's saying the slope is 0. Like at this point, the slope is 0. Okay? And that's because it's not only continuous, it's not only differentiable, but also f of a equals f of b, meaning this y value, let's say this y value is 3, is also the same as this y value at the end, 3. So at some point, if I'm traveling along the line, I have to go back down to hit 3 again. Or maybe if I'm going down first, I have to go back up to hit 3 again. Meaning either way, there is a point on the graph where I'm flat, where I have a horizontal line. And we know if I have a horizontal line, that means the slope equals 0. That's why Rolle's theorem says, Rolle with the O, that the derivative at some point has to equal 0. Okay, so again, the only difference here is there's 3 conditions for Rolle's theorem. It's continuous, differentiable, and f of a equals f of b. Meanwhile, in mean value theorem, all you got to say is it's continuous and it's differentiable. I'm putting a star here. I would put a star in your paper because this usually shows up in the AP exam. Alright, so after this horizontal line, I put AP problems related to continuity. Okay, so this is a good place to pause the video and try some problems before you play it again and see some of my solutions. Okay, I'm going to go over some of the AP problems that I put on this worksheet. Alright, number 13 says, the graph of a function f is shown above. At which value of x is f continuous but not differentiable? Now, if I see these keywords, I'm going to immediately write to myself, pointy part of the graph. Okay, so I'm looking for a pointy part of the graph that's continuous but not differentiable. All right, let's see. I have a few choices. There's A here. Let me check A. A is right here. Is it continuous? Yes. Is it not differentiable? Yes. So I know that's an answer. Voila. You have it. I mean, you can check the other problems. So if I look at B, B is right here. There's a problem at B. This is not continuous. B here has a hole. Okay? So obviously, immediately I have to eliminate that choice. Let's look at C. C is continuous, great. But is there a pointy part at C? No. So C is continuous. And it's also differentiable. Which is cool, but that's not what the question is saying. Let's look at D. So D, it's not continuous. And if you remember, that type of discontinuity is called a jump because I am jumping. And at E, it is continuous but also differentiable just like C. Okay? So A is the right answer. Next question. I have a piecewise function here. And I have to see if the limit as x approaches 3 exists, if f is continuous at x equals 3, if f is differentiable at x equals 3. Okay, let's check all of these things. So first off, this means that x is smaller than or equal to 3. That means 3, 2, 1, 0, negative 1, negative 2, negative 3, etc. These are the x values that apply to the first function. For the second function, the x values that apply are 3, 4, 5, 6, 7, 8, 9, 10. And I made a small mistake. 3 is not included if we're trying to be specific here, because it's only greater than 3. Okay, so for a limit to exist, let's check the first one. The limit from the left has to equal the limit from the right. Okay, of this function. So of f of x, f of x. Well, let's see. From the left, I'm going to use x plus 2. So I'm going to check the limit as x approaches 3 from the left of x plus 2. I got that here. And I'm also going to check the limit as x approaches 3 from the right of the next function, 4x minus 7. Now, if you're wondering how I decided that, from the left, the numbers on the left are 3, 2, 1, 0, negative 1, negative 2, negative 3. That's why I chose x plus 2 on the left. On the right, the x values are 4, 5, 6, 7, 8, 9, 10. That's why I chose 4x minus 7. Now I simply solve. I plug in 3 plus 2. I'm going to get 5. If I plug in 4 times 3 minus 7, I'm going to get 12 minus 7. I'm going to get 5. Is 5 equal to 5? Yes. So the limit as x approaches 3 exists. Okay? So I know 1 works. So I can eliminate some choices already, A and C. I'm down to B, D, and E. All right, now I have to see if f is continuous at 3. If you remember, to be continuous, if you think about it, if I have a graph at 3, then there has to be no holes, no vertical asymptotes, no jumps, okay? So on the left side, I have x plus 2. Let's say the graph looks like this, and it ends at 5. On the right, it's 4x minus 7, so it's still a line, and it still is at 5. So since both of them land at 5, or meet at 5, when x equals 3, it's continuous. So I know 2 is also an answer, so I'm going to cross off B. I'm left with 2 answer choices. Now the good thing here is, because of the new standards of the AP exam, there will only be 4 multiple choice options in all the multiple choice problems. So I just wanted to make that clear for everyone. Last thing, f is differentiable at x equals 3. So this is a bit, you have to think, differentiable means I have no pointy parts. No pointy parts. Okay, there's a few ways you can go about this. You can look at the graph and say, well, this is linear from both sides. And the slope on this side, the slope, okay, or the derivative over here, if I take the derivative of x plus 2, the derivative is 1. So the slope here is 1. And on 4x minus 7, if I take 4x minus 7, if I take the slope of that, it's going to be 4. So that means the slope of this line is 4. And since they're linear, okay, you're going to end up having a pointy part right here, and the slope on the left is different from the slope on the right. So it is not differentiable, not differentiable. Okay, because the f prime of x on the left, or the derivative, is not equal to the f prime of x on the right. To make it formal, you can put limit as x approaches c from the left, limit as x approaches c from the right. Okay, I'm only writing this extra stuff down because we need to use that for free response problems. Okay, for multiple choice, obviously you don't need to write that down. So 3 doesn't work. So my final answer is D. Number 6 is a very similar setup. I have to check everything. If f has a limit at x equals 2, if f is continuous, if f is differentiable. Okay, so I like to usually just look at the first situation here and put it over here, x squared minus 4 over x minus 2. What I got to do is check if it has a limit as x approaches 2. Limit, okay, limit, that means from the left and from the right, or I can just try to plug in. Well, let me see, this is not going to work out. If I plug in 2 right now, I'm going to get 0 over 0, which we do not like. So I can either factor and cancel, or do L'Hopital's rule. So if I do L'Hopital's rule, just for the fun of it, the top one is going to be 2x, and the bottom one is going to be 1. So I'm going to have limit as x approaches 2 of 2x. Then I simply plug in, and my limit is actually 4. So the limit is there, so the limit exists. Yay! Cool. Now, is f continuous? I usually like to graph things if I'm just so I have a visual. So the second function says at x equals 2, okay, my y value is 1. So let's say I have a little 1 dot here. But then we're saying that the limit is at 4. So that means if I graph this, I don't know exactly what the graph looks like right now, right? And if I wanted to figure out what the graph looks like, I can go back to my original function. I can factor the top, see if it has any common factors in the denominator. Oops, there is 1. I'm left with x plus 2, so I can graph x plus 2. That means I start at 2 with a slope. That means I do meet at 4, but there's a hole there. And I know there's a hole there because I canceled x minus 2 from top and bottom. And also, there's this little guy right here that tells me at x equals 2, my y value is 1. So that's 2 comma 1. If I look at this picture, is that continuous? It's not. Okay, there's a hole. So there's a hole. And unfortunately, the hole is not filled in. Like if this little dot here was inside the hole, then it would be continuous. But it's not. It's outside, right? So f is not continuous. Okay, and if I'm not continuous, I am not differentiable. You can look at our notes above to check that. Great. So my answer is A. Okay, so some free response problems from 2011, number 6. F is a function given by this piecewise right here. So x is bigger than or less than or equal to 0, so that's 0, negative 1, negative 2, negative 3, negative 4, etc. X is greater than 0, that's 1, 2, 3, 4, etc. Okay, to show that f is continuous, this is what you always set up first, okay? You have to show that the limit on the left at 0 of f of x should be equal to the limit on the right of f of x. They should be equal, okay? If they're not equal, then you say it's not continuous. If they are equal, then they are continuous. So let's try it. I'm going to do the limit from the left of 0, and the function I'm using is 1 minus 2 sine of x. And you can look above at my x values to see how I decided that. And then the limit on the right of e to the negative 4x. And all I got to do is plug in 0. 1 minus 2 sine of 0. Sine of 0, this whole term will be 0. 1 minus 0 is 1. Here I plug in e to the negative 4 times 0. That becomes e to the 0. Anything to the 0 is 1. Is 1 equal to 1? Yes, it is. Okay? So you say, yes, f is continuous. Because the limit as x approaches c on the left of f of x is equal to the limit as x approaches c on the right of f of x. I know it's long, but please write it down because this is a free response problem and you need to write a full sentence down. Same thing over here. This is a calculator problem, so I just want to note this is a calculator problem. Oops. So you can type this in the calculator and see if it is continuous. Same steps. So I'm going to say limit as x approaches c on the left of r of t. Is it equal to the limit as x approaches c? Well, c here is 5 specifically, right? So 5. 5 from the right of r of t. Okay? So from the left, I'm using the limit as x approaches 5 from the left of 600t over t plus 3. You can read the problem and make sure that you understand where I got this function. and check the limit as x approaches 5 from the right of 1,000 e to negative 0.2. See, now you're going to plug in 5 on both functions. Go ahead, you have a calculator. And see if the values are the same. When you do that, you're going to see the values are not the same. So you're going to say r of t is not continuous at t equals 5 because the limit as x approaches 5 from the left is not equal to the limit as x approaches 5 from the right. And don't forget to put r of t. I always forget that. R of t. Okay, this guy is the same situation. Is f continuous at x equals 3? Again, I'm going to write it. We have to check if the limit as x approaches 3 from the left, is it equal to the limit as x approaches 3 from the right? Okay, so from the left, I'm going to do x approaches 3 from the left of square root of x plus 1. I'm going to check limit as x approaches 3 from the right of 5 minus x. I'm going to go ahead and plug in. This will equal 2. I'm going to go ahead and plug in. This will equal 2. So they are equal to each other. I'm going to say yes. F is continuous at x equals 3 because, you know it, the limit as x approaches 3 from the left is equal to the limit as x approaches 3 from the right. And again, don't forget the f of x like Miss Mimi does. Great. So as you saw, I gave 3 free response questions that ask the same exact thing. Is f continuous at x equals 3? And for every single one of them, we did the same thing. We checked if the limit exists, meaning is the limit on the left equal to the limit on the right. Okay, so now I gave you the pages for the Barron's book practice. Please try them. Okay, it's useful. It uses a very similar language to the AP exam. You have the solutions and explanations given on pages 110 to 112. Okay, you have this resource for you. So this is a good time to practice those problems. Okay, I gave you a closing question. Let's go over it. Which of the following values of x, given this function right here, is it not continuous? Meaning, where are the problems? Okay, well, if I rewrote that, I have 2x minus 2's at the top because of the squared. And I have an x minus 2 at the bottom and x plus 1. Okay, so I can see I have a common factor, x minus 2. I can cancel the common factor. That gives me a whole at x equals 2. Okay, so I know 2 is a problem, so I know my answer should have a 2 in it. I'm going to eliminate some choices. So I eliminated A, eliminated C. Now, x plus 1, that's a vertical asymptote. So I know that's a problem. So my answer should have a negative 1. Now, x plus 3 here, that's not a problem. That's just a 0. And we learned that in algebra, it's okay to have a 0. Right? That's not a problem. Not a problem. That just means at negative 3, you have a dot there. And that's not discontinuous. That's a real solid y value. Okay, so the answer is D. I'm going to pause here because I copy-pasted the AP review packet problems that relate to continuity. Meaning you can do these problems. 15, 25, 83, 90, 5. Okay? And then on the mock AP exam, I also copy-pasted the problems. Number 77, 82, and number 6. You can do these problems now. All right? So I need you to go ahead and retry them. I'm going to make the next video to answer these problems. All right, scholars, good work.